Utilization of machine learning in recognition of rocks and mock mines by sonar chip signals. The goal of this work involves the application of machine learning methods and models for the recognition of objects underwater based on sonar chip signals. Specifically, the main goal is to create a classification system that is able to distinguish signals corresponding to rocks from those associated with mock mines. Tasks include collecting and preparing input data, analyzing and processing sonar chip signals, developing and optimizing a machine learning model using methods to reduce overtraining, and evaluating the results. This work is aimed at solving the urgent problem of recognizing objects on the seabed and using advanced technologies to ensure safety and research of the underwater environment. In this study, a diverse set of machine learning algorithms has been employed to discern patterns and classify sonar signals. The algorithms chosen demonstrate versatility in handling the complexity of the data. The following algorithms have been applied: decision tree, Gaussian process, Laplace approximation, k-nearest neighbor SWOT, logistic regression, multilayer perceptron, neural network, random forest, etc. In order to assess the effectiveness of machine learning models in the recognition of rocks and mock mines using sonar chip signals, a comprehensive set of experiments was conducted. The dataset utilized for these experiments was the connectionist bench Sonar Mines vs. Rocks, obtained from the UCI machine learning repository. The raw sonar chip signals, which are numbers between 0 and 1, were used directly, as all the data was numerical and had the same ratio for values, and the dataset was divided into input X and output Y variables. Label encoding was applied to convert categorical labels, rocks and mock mines, R and M, into numerical values, 0 and 1. The synergistic effect of combining dropout and L2 regularization was investigated. Models with different dropout rates and regularization factors were assessed to find the optimal combination. The robustness of the models was evaluated using k-fold cross-validation with stratified sampling to ensure representative splits. It is worth noting among the results that neural networks with dropout and L2 produced the greatest accuracy, 88.45%. Dropout accuracies. We can see here that 0.3 weight has produced the greatest accuracy of 87.64%. L2 regularization accuracies. Here we can see that the greatest regularization factor was 0.001. ADA boost summer with decision tree yielded a moderate accuracy of 71.12%, showcasing the ensemble's ability to improve classification over individual weak learners. ADA boost SAM with logistic regression showed a significant boost in accuracy to 79.76, underscoring the adaptability of ensemble methods to different base classifiers. ADA boost SAM with random forest achieved the highest accuracy among ensemble methods at 87.50%, emphasizing the robustness of combining weak learners. A decision tree alone exhibited moderate performance, 73.52%, but employing minimum cost complexity pruning resulted in a slight decrease in accuracy, 75.21%. This emphasizes the delicate balance needed in decision tree complexity for optimal performance. Logistic regression, with its inherent simplicity, demonstrated competitive accuracy, 76.48%. The introduction of L1 and L2 regularization, however, did not yield significant improvements, emphasizing the stable nature of logistic regression for this classification task. Multilayer perceptron demonstrated robust performance at 80.31%, showcasing the power of neural network architectures for complex tasks. Neural network with dropout, a technique to alleviate overfitting, achieved an accuracy of 84.21%, indicating its effectiveness in improving generalization. Neural network with L2 regularization, while effective, demonstrated a slightly lower accuracy at 77.90%, suggesting that dropout might be a more suitable regularization strategy for this task. The combination of dropout and L2 regularization in the neural network exhibited, as was mentioned before, the highest accuracy at 88.45%, highlighting the synergy between these regularization techniques. Random forest performed exceptionally well with an accuracy of 85.57%, making it a robust choice for this classification problem, considering that random forest is a simpler algorithm than building an entire neural network. Conclusions. The utilization of machine learning for the recognition of underwater objects using sonar chip signals has proven to be a promising avenue for distinguishing between rocks and mock mines. Through a systematic exploration of various machine learning algorithms and techniques, valuable insights into the effectiveness of different approaches for these classification tasks have been acquired. The experimental results highlight the varying performance of the employed algorithms. Notably, ensemble methods such as SDE Boost SAM with a random forest-based classifier demonstrated superior accuracy 87.50% compared to other standalone classifiers. Neural network architectures, including multilayer perceptron models, exhibited competitive performance. The application of regularization techniques such as dropout and L2 regularization showcase their effectiveness in mitigating overfitting, especially evident in the neural network dropout and L2 model, which achieved an accuracy of 88.45%, the highest one. This method can be effectively used for various demining operations. Ensemble methods, by combining multiple weak learners, demonstrated robustness and improved generalization. Thank you for your attention.